This is the last section of chapter 8, improper integrals. Right, so what's improper integral? So far, we have learned to integrate the functions, and all those integrals are called proper. And so if you notice all the integrals that we have looked at, the integrals is actually, the functions are continuous, okay? Now, in this case, we will look at the improper integral. Sorry, the definite integral. So that is the integral that have upper lower limit, right? So it's from 2 to 5. Something, right? So the x natural log of x dx. So this is the integral. Now, if you're gonna grab the function x natural log of x, you notice that it will be continuous on the interval from 2 to 5, and so it's proper, okay? But then you might end up with functions or the integral that is not proper. In this case, I'm trying to show you, instead of from 2 to 5, we're going from 1 to 5. Now there's a big problem here. You may not notice, if you grab these functions, xl and x, you notice that it's not continuous at 1. Well, how do I know? If you plug 1 in, you can see, well, I think my bad. It's 0, right? So I think 1 is still fine. But if you have from 0 to 5, then natural log of 0 is 75, right? So you can take the log of 0. And when you graph it, what you would see is the graph will have vertical asymptotes at 0, okay? And so your graph will be kind of as a holes here, looking at the definite integral of the area underneath the curve, and here is a little bit weird, okay? So in that scenario, the integral is improper. Okay, so there are two types of improper integrals. One is the function is discontinuous. Okay, discontinuous. And another type of this improper integral is when the limits are infinite. So what do I mean? Instead of going from 0 to 5, right, you can have 0 to infinity. Okay, 1 over x squared dxa. So in this case, if you graph, this is 1 over x squared, and when you can integrate from 0 to infinity, we're looking at the area, okay, from 0 to infinity. So basically this area, okay. So you see that's kind of a bit weird. There's a gap here, there's a gap there. So now when you look at these type of improper integral, there are two different type of answers. One is if this gap is big like this, then we ask the question of whether the area here is finite. Well, if this area is too big, you see, because go on and on. So there's a possibility that this area is huge. That means it's approach infinity. In other words, if I ask you to paint these regions underneath the curve, you would say you can't do it because it took infinite amount of paint to do it. It's not possible, right? So that is one scenario. And in that case, we say the integral diverges. Okay. Then in the second scenario is, well, it is finite. It's really, I mean, even though it's a gap here, gap there, but it may come out to be 5, 10, 20 as an area. So in that case, we say it converges. Okay. Right. So let's dive into the two type of improper integral here. All right. So let's look at the first type. This is called type 1, the infinite intervals. So in the infinite intervals, the graph, you see we're going to integrate from 1 to infinity, 1 over x squared dx. If we're going to graph this, again, you should do the C. You can graph on the calculator to see it, but it's not hard to see. Right, so you graph 1 over x squared, go like this, this. Okay. Now, since I integrate from 1 to infinity, it's here, 1, infinity, out here, there, right? So again, what I'm really asking you to do is to integrate and find the area. So the 1 to infinity, all the way. Okay, so it's that area. Now we have a challenge here. First, because it's infinity, it's upper limits. So you cannot use the fundamental theorem calculus. On the one that you find the entire group like an upper and lower limit, you know, the upper limit is not even a number. Okay. So the way we do is, instead of going from 1 to infinity, which I cannot do directly, we would go from 1 to an arbitrary b. So let's say from 1, 2, 3, or 5, or 7, right? I'll call them b, arbitrary. So can we integrate from 1 to b? Can you find the area from 1 to this? Yes, I could. Now that is become proper, right? It's normal. I'll do that. Okay, so I can certainly do that. So that's why first step we calculate the interval or the integral from 1 to b, 1 over x squared. Now, so this is a proper integral. I can find the entire derivative of these functions. We write it as x to the -2. Using the power rule, you add 1, which is x to the -1 over -1, right? So now you have -x to the -1 from 1 to b. I think I should have drawn a graph at different places, but negative, so you have -x to the -1 over -x to the -1 from 1 to b. Okay, that is -x to the -1 will be right. It's -1 over x, right? And then you plug in 1 and b. Plug in b, you have -1 over b, and plug in 1, you have -1. Okay, but I think it become a +1 there, so we subtract 1. So after all, this part right here, when you integrate, it become 1 minus 1 over b. This is the plus side, by the way. Okay. Now I have the area from 1 to b. Okay. So let's say if b is 10, then the area is 1 minus 1/10, so that's 9/10, or 0.99. So the area from 1 to 10 underneath the curve is 0.99. let's say if you move B out to 100s, right? If B is 100, then what? If you go all the way to 100, so 1 to 100 you plug in here, then the area will be 1 over 1 minus 100 is 9900, so 0.99. Then you move the B further, so we have thousands, then that'll be 1 over 1000, and that become 0.999. So what do you think if B approach? If you think what happened if B approach infinity, you can see this number getting closer to 0.999 and 0.99999, 0.99999. So it's actually approaching 1. And you can see, in fact, from the formula here, as B approach infinity, you see that approach 0, right? So the number getting larger and larger, so that will approach 1 in the end. Okay, so basically, as B getting larger and larger, this is where the limit notion comes in, right? So if B approach infinity, so in order to go from 1 to infinity, then you let B approach infinity. Okay, so now we do the second step is to take the limit where B approach infinity. Here, right? Take the limit as B approach infinity, and now this integral is replaced with this integral limit B approach infinity. So this is our answer over here. If you take the limit B approach infinity, let's go to 0, so it's equal to 1. Therefore, we say this integral converges to 1. So what we mean is this improper integral turn out to have a finite values. It's precisely 1. Okay. Now let's look at the next example. Before I get the next example, notice this is the case when the upper limit is infinity, right? We could have the other way around where the lower limits could have been negative infinity approach, and then the upper limit is maybe a positive or negative number here. So we could have negative infinity on a low limits, or we might even have negative infinity to positive infinity. That's an extreme case. So here's the 3 cases. Case 1 is when you have infinity, like we did. You see that we could do it by replacing that with B, arbitrary number B. Then we take the limit B approach infinity. If we have negative infinity on the lower limit, then we replace this with an arbitrary constant A. Then we take the limit A approaching infinity. And in the last case, if we have to go from negative to positive infinity, we split that into 2 integrals. From infinity to C, then from C to infinity. Then from here, it's really case 1 and case 2 combined. Okay. Let's look at an example. All right, so in this case, you see we go from 0 to infinity. Well, again, I can't do it. So what we're going to do is we will have to do it in 2 steps. Okay, so we're going to replace the infinity with an arbitrary constant, and then we let the arbitrary constant approach infinity. Right? So that's the way we do. Now, again, example 1 here. Let me label it so we can easily reference. Right, so here's example 1. Right, so with example 1, this integral from 0 to infinity uh, 2x over x squared plus 1 dx. Because infinities is the not a number, so we'll replace infinity with an arbitrary constant b. Then we take the limit and b approach infinity. So technically we have 2 steps there. However, if the integration, so finding antiderivative is easy, we kind of do it in one single step here, right? Limit integral. In this case, I can do because it's pretty straightforward. What's antiderivative of 2x over x squared plus 1? So if you observe carefully, the denominator is x squared plus 1. What's the derivative of x squared plus 1? 2x. So see that there, we actually have the form u prime over u. And the answer is natural log of u, right? So here I have just the natural log of the x squared plus 1. And then from 0 to b. So that is really limits b approaching infinity from 0 to b. Right, and then we apply the upper lower limit, plug in. Then we have natural log of b squared plus 1 minus the natural log of 0 squared plus 1 from b approaching infinity. Notice that as b approach infinity, this constant will be approach infinity, this number getting larger and larger, the natural log is approaching infinity. We don't have natural log of 1 here, natural log 1 is 0. So you see that as b getting larger and larger, the whole thing getting larger and larger, so it approaches infinity. And in this case, the integral diverges. Okay. Now, if we look at example 2, okay, this is where you see the negative infinity appear at the lower limits and upper limit, right? Well, we're going to handle it the same way. But instead of replacing the upper lower limits, we can be replacing the lower limits. So we got from negative infinity to 0, x e to the x dx. Okay. So what I'm going to do, replace negative infinity with any arbitrary constant. I like to call it a. You can replace anything you want. And then don't forget that the a now will approach negative infinity. For it to be equivalent to this, the upper limit is not b, but in this case, it's 0. Okay, so 0 here, and then x times e to the x dx. Okay. Now, notice that the in this case, what's antiderivative x e to the x? You see that one is not easy because I don't know what's antiderivative x e x. So to figure out the antiderivative x e to the x, you go back and use the integration technique that we've learned. In particular, here I try to integrate this on the side. So one is antiderivative of x times e to the x dx. Well, don't forget that this is a polynomial times exponential function, so the integration by part worked very well. U dv. Remember u dv, according to the limit, this is polynomial x. So u is going to be x, that's exponential, that's e to the x. So you take a derivative of u, it's 1 dx, and that becomes still antiderivative of x is e to the x. So you can see using, again, by parts formula, then this integral will become u times v, that's x e to the x, minus the integral z du, that's e to the x times 1 dx. But the antiderivative of e to the x is e to the x, right? It doesn't change. So it turned out to be x e to the x minus e to the x plus c. And this part right here is kind of doing on the side to figure out what is the antiderivative of x e to the x. Okay. Of course, now one after I found it, then just apply the fundamental theorem of calculus. That would equal to the limit a approach negative infinity, and then from a to 0. Actually, I integrate this, so don't leave the integration symbol. It is x times e to the x from a to 0. Okay, then I plug 0 in. That is limit a approach negative infinity. Plug 0 in, you got 0 minus a x to the a. Right, so plug the upper limits, and then I plug in the lower limits. Well, x approach negative infinity. Okay. Now x approach negative infinity. If you rewrite this, let me rewrite that to make it easier. And we write that as negative a over e to the negative a. Right. Once you plug 0 in, so that's gone, and plug this one, you have a e negative a. Now you're going to ask yourself, as a go to negative infinity, what's the numerator approach? Negative infinity, negative, so it should approach positive infinity. The denominators is also approach e to the infinity, right? So that's still infinity. Right, so since they both approach, numerator and denominator approach infinity, we can use the L'Hopital rule to finish. And that is, take the limit, a approach negative infinity. What's the derivative of negative a? I think of that as a variable, right? Negative x will be negative 1. And the derivative of e to negative a is e to negative a times -1, like that. Okay. I'm using the L'Hopital rule. So that's -1, -1. And if you look at this carefully, as a approach infinity, this is approaching infinity, so make it positive. So the denominator approach infinity, and hence is equal to 0. Actually, zero a. Okay, so something is not right. Let me check. Negative a is -1. That e to the negative. Oh my bad. I don't know why I said 0. It's too sleepy now, actually. All right, so wait, all right, sorry guys. Apparently, it's a big mistake. He a bit sleepy, half sleep. When we record this video, this is apparently not the right antiderivative. Right, the antiderivative is x e to the x minus e to the x. Right, so just even from here, it's wrong because I have. The antiderivative should have an extra minus e to the x there. That's from a to 0. Okay. So when I plug in, right, so all of these is wrong. All of this, we have an extra term there. Right, so when you plug 0 in, it's now 0 minus e to the 0 is 1. Then subtract a e to the a minus e to the a. So here still have, that's a -1, negative a e to the a plus e to the a. Now as a go to negative infinity, this go to 0. Let's go to 0. And that one go to 0. So what I'll have left is -1. Actually, we're using L'Hopital rule here, and you should get 0, and the answer is -1. Okay. So it's equal to -1 as the final answer. Okay. That finished the first part of 8.8.